Okay, so we start another round of discussing how to think about those flows. And okay, so today I will go through a draft that is in the making. I'm rewriting the manuscript because on the way I realized that focusing on flows was reflecting more my learning curve and not what we actually would do on devices. Those flows are very beautiful and they are fascinating and elegant, but for what I know, we are not going to be meaningfully able to implement them properly and so on. And as I was studying how to do the flows, I started discretizing the flows, and then we get those double bracket iterations. But immediately when I started running some numerics, I started wobbling the durations. So basically at every step, I thought, okay, let's make a greedy strategy and try to see what will happen. So we saw this in the previous tutorials when I was handwriting. And today I want to start with directly this, which is my attempt of defining double bracket iterations in words, and then I will give some abstract algorithms just to be clear. So our story will always start with the input Hamiltonian, so that will be H0. And we want to prepare some state related to it, maybe diagonalize it, but we were talking about how costly it might be because it's a large matrix with very small gaps. So we need to think about what will be going on there. But double bracket iterations just means if you schedule a double bracket iteration with me, give me diagonal operators, and then give me also step durations, and I will start running this. So let me start with K0, then this is H0, and this will be HK1, where I take the first bracket using the first diagonal operator and the input Hamiltonian. I form the commutator, and that becomes the generator of the evolution. And then here I'm discussing all the things we were saying, that this is a unitary operator. I can study this rotation in its own right, whether the off-diagonal terms here decay and whether I'm doing a good job. So the first step is take your Hamiltonian, take some diagonal operator that you like. You form the first bracket. So H0 will be rotated by W0 with timing S0, and we get the first Hamiltonian. So once I have the first Hamiltonian, let me clear, the new zoom is different. Once I have the first Hamiltonian, I can input here H1. I can take a different diagonal operator. How to choose those diagonal operators is currently our research effort to try to answer this meaningfully. This answer usually will have only constructive attempts that will be quite heuristic, might not be optimal. The reason is that this is a big matrix. This is also a big matrix. How do you find it properly? We might need to resort to some heuristics, and that's fine because in the end, those devices are available. So we can also get lucky and get very nice sequences of D0, and who knows, maybe we will get good state preparations. So we defined H1 by that previous rotation. So now we again rotate, and that will give us H2. And we iterate like this. So this is what I call a double bracket iteration. Double bracket is because if I rotate by a W operator here, if I look, so this is already a solution because here, notice that I'm not changing the W bracket in the duration from 0 until SK. This is a constant Hamiltonian that I could view as AWK, and this is like some Hamiltonian QK, yeah? So we could think of this as a Hamiltonian. So this is just the solution of this time-independent Schrödinger equation with this generator IW, which means if we put it here, we will start seeing this equation being in some way a little bit like a Heisenberg equation. Okay, so that's why we call it double brackets, because we are choosing those brackets here, IW is like a Hamiltonian, as I keep stressing. So when I will look how this evolves, this looks like a double bracket. Okay, so we have this double bracket. And for any commutator, any operators here, that will be a double bracket iteration. But if I want to do diagonalization, I will have a diagonalization dBi as soon as I start choosing diagonal operators. So that's one thing that is a subtlety. And the structure of those variational operators that we choose here needs to be informed by some insight. And that's telling you what this dBi, this double bracket iteration, will be doing. If I choose them diagonal, we will discuss now, then this diagonalization, this dBi will be having diagonalizing properties. That's why we do it that way. Okay. So that's dBis. And I want to continue and like add layers of refinement of like what it means more to be doing those double bracket iterations. So that's supposed to be intuitive, but then we can double up on it and see what's going on. I have a couple of comments on what it means to do diagonalization in quantum computing. And specifically, this will be relevant for showing how to implement those double bracket iterations. So when I tell you, okay, this will be successively always, making steps towards to approach diagonalization, then I give you some prescription, okay? And how do you use this prescription? One way is to do something similar to variational quantum algorithms, variational quantum eigensolvers, to apply a certain circuit to a state. And I will refer to this here for now as eigenstate by eigenstate. Okay, so what dBis give us, if we collect those unitaries together and get some unitary U, it gives us an approximation to the exact diagonalization unitary. So if my input Hamiltonian H here is rotated by this exact unitary, I get some H infinity, which is diagonal. So it means that I can use this unitary here to apply it to some state, mu, okay? And then if I apply the beginning Hamiltonian, I will see that I can add some unitary identity, and then it will be an eigenstate grid, just because this is diagonal. Okay, so that's what I mean eigenstate by eigenstate. If my quantum computer is initialized in some computational basis state, so a simultaneous eigenstate of Pauli Z, which we choose diagonal, then I can apply this diagonalization unitary, and the resulting state will be some eigenstate with energy E mu. Okay, and I can do this eigenstate by eigenstate. So in some way I diagonalize, yeah, because I have a machine that can prepare me any eigenstate that I choose. I just need to choose the eigenstate. Akash, I see your raised hand. Well, can you say the question?
Yeah. So I have this like question because you had this equation, right? With the first one.
You're a bit muted. Can you
hear me right now?
Yep, say again.
Yeah, so you had this equation in the beginning, right? With SK, WK, the first flow equation.
Sorry, say again.
The first flow equation, can you open the paper? Yeah.
Yeah. Okay, here?
I cannot see it. Maybe.
Yeah, starting now.
Yeah, exactly. So if you go up there, no, let me see. No,
So
I can't see anything.
We had the double bracket iteration.
Yeah, exactly.
Yeah.
Yeah. The number one equation, you had this SK. So what do you mean by you are choosing SK variationally? Do you mean that you're optimizing the SK at each K, or you're just choosing the SK like, at each K step, like, randomly or something like that? Because I think that, like maybe at each K, there is some optimal amount of duration you have to do this kind of thing, right? Yeah.
Yeah, okay. So let's go to some numerics maybe to answer that question. And to answer that question, we can look what's happening to some Hamiltonian H if I rotated it by the corresponding bracket W, and I rotate it to some timing S, which I will be changing here on the off diagonal. Okay. And I will be looking at the measure, the off diagonal part of that double bracket rotation of the input in Hilbert-Schmidt norm because of the monotonicity relations that we were discussing. And the blue curve is the double bracket rotation, which we were just looking at. So let me write it here. W would be my D operator, diagonal operator, input Hamiltonian. If you want, we can put zeros below, or we just say I will be taking only one step, so it's just H, 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 H. Yeah, maybe I should fix the notation there for the paper. Okay, so in this notation, there's W and H. Now I can define the H sub S or H of S to be just the rotation generated by this Hamiltonian of that Hamiltonian. And so this is a function of S. So there is S dependence I can check, and I can check what's happening if I look at the off diagonal of HS, and I take this. So here I can by brute force check, given conditioned on a choice of D, what is the maximum reduction from 1 to 8 to 95 of my rotation, and that would happen for this time 004, let's say, S004. That's my minimum. So basically it's a greedy thing. It's like I have some Hamiltonian, it's some Hamiltonian H, it could be some Hamiltonian HK after K recursion steps of the iteration. And now HK tells me that I can construct the bracket WK with some variational choice of DK. I'm not discussing here how to do this because this is where the problem specific stuff comes in. Yeah, so you need to have some strategies for choosing that. But it could be just a magnetic field. Yeah, so it can be quite a simple operator. We could choose, for example, we could choose DK.
Yeah, I mean, I have seen this plot and I also like a bit confused because what I'm saying that considering the x-axis you have like duration S, right? Does this S means that at each S step, consider step duration, you're running the diagonalizing algorithm again, right? Like you're initializing maybe with 0.04 and you're running the algorithm maybe once, and then you're checking, okay, at this particular value, I have this 95 of diagonal.
Yeah.
At each point, you're running the algorithm again and again, right? It's not like a continuous flow of the same algorithm.
So those plots are done for like a few qubits, like 9 qubits or whatever. Yeah. And here I'm using the possibility of doing this in Python on my laptop, just run this. Yeah. On a quantum computer, you would have to, be resourceful with your runtime. But in principle, you can imagine that you have this HK Hamiltonian and you use it to implement the flow for a sequence of S functions. And after each S that you chose, try to measure this function in some way. In principle, you can do this, no?
Yeah.
And then you would construct by quantum simulation or whatever. You run this kind of you run this many times, and at some point you will start constructing this kind of curve. And because it's noisy, maybe it will start looking like that. Yeah. And those are your measurements with some error. You fit a parabola, you look at the apex of the parabola, and you say, okay, my S rotation, according to what I know, is this. You might have some error mitigation that I was just discussing with Matteo. Then you extract it here, it maybe moves a little bit, and you get here, and you say, let me schedule the step to have this value. Okay, so that brings us to one point. I'm not sure if I'm calling this the classically instructed Yeah, okay. So I think I describe it as classically instructed double bracket iteration, but the way I define the diagonalization DBI is like you want to do k steps of k recursion steps. So you need to tell me how long you want me to rotate in each step and what are the diagonalization operators, so those decay operators. So you might give me some strategy to do this. So I'm speaking here of a diagonal association map, which might be a map which is doing a closed loop optimization. It might be some randomized Monte Carlo. It might be some strategy of you interacting with your device. But then let's say, given your schedulings, I will be using your map to define me for HK. I ask your map for this Hamiltonian, what decay you choose. I take that decay. And then this decay together with HK gives me the bracket in equation 2. And I just rotate by the time S that you told me. Okay? So this is more like an invitation for you to use this algorithm. And I can tell you some things about how to choose those things, but I cannot give you the optimal answers because this is problem specific. Yeah?
Right.
I'm not sure if I answered the question, but this is roughly what I'm trying to say. So it needs to be classically instructed, or how do you say, is maybe a supervised diagonalization iteration where you can imagine that you sit in your Kibo operation room and then you keep scheduling, you check after 5 recursion steps, what did you get? And then you say, this informs me that for this 200 qubit Hamiltonian, after 5 steps, I should choose maybe S equals S5. Let's say S5, I should choose S001. And my operator D1 is maybe some magnetic field where I have BI and ZI. And those BIs maybe wobble like this. This is 200 qubits. I is like number of qubit, and this is BI, right? So I choose some values here for those things. As soon as I have this operator, let's say D5, I can make another step to define for me H6. And then I repeat it. I could construct this on the fly in principle. I could also try to do some theory and maybe add them. But what we know is that there will be those diagonalizing properties. So even if you choose a bad ansatz, plus minus that ansatz will make a diagonalizing direction for you, either in this direction or the other direction. So how do you choose plus minus? You run very quickly something and you check whether some energy fluctuations are going up and down. So you check it in 2 directions and you schedule maybe 100 runs. And quickly you will start seeing, okay, I started improving. Okay, that's the direction. So now let me try different S rotations. So if I go longer, am I improving it further? And at some point you see, oh, I stopped improving. Let me go back. That's my S. That could be some strategy. So it would be a closed loop optimization to build this on the fly. So you have some diagonalization association. So in the step HK, I associate this operator because that's my strategy. And it's all about optimization now.
Yeah.
So basically those double bracket iterations facilitate diagonalization conditioned on your optimization strategy, and your optimization strategy will depend on your device. And it will depend ultimately on the input Hamiltonian, so Heisenberg or model or some high energy model will have a different kind of scheduling, and different devices might have different measurements available and so on. So you might use other optimization strategies there. Okay. So that's how it will be done. And ultimately, you would be applying this to some computational basis state in the beginning because that's the simplest thing to do. Double bracket iterations are a way of constructing unitaries. You give me a Hamiltonian, I construct a bracket. That bracket gives me a unitary. And if I compile this using Hamiltonian simulation, I get a circuit. So if I have the circuit, I can apply it to a state. And you see, this is very similar situation like variation quantum eigensolver. The only difference is that the unitary that the DBI prescribes were rotations of the full Hamiltonian. So in principle, in the beginning, this double bracket iteration is a global method where for every input mu, I don't change the iteration, and it's a global eigenstate by eigenstate. While if you do variation quantum eigensolver, given some input, you might be changing your circuit because you might be targeting a different eigenstate. Yeah, so just more flexibility. And often flexibility is not the best thing because you might be stuck with the number of possibilities. So who knows? In the end, we will see, for example, here numerics. So let's say I run my double bracket iteration for some steps. Let's say I have, let's see. I'm getting used to the new Zoom. So in the beginning, I had 150 on 9 qubits. So I will be applying this to different states. And now in panel A, I can do 1, 2, 3, 4 steps. That's not too costly. This is by all means very realistic to run this for any setting that this is not costly yet. Yeah, so you just run this. So you found that there's a norm 64 of the off diagonal. So there's still quite a lot of on the matrix. So if in the beginning it was diagonal and a little bit on the off diagonal, you rotated this to H5, and there will be like a little bit less, but still this stuff has measured 60. Okay, pretty bad. But what can happen is after 5 steps, so here I have 10 steps, in the middle I have 5 steps, you see that the reduction for this fully polarized state after 5 steps, the outside of this is the energy fluctuation. So that's a measure of how good this is as an approximation to an eigenstate, and it's already great. So when I run this for a small number of steps, it might be also a local method, because whatever this DBI is, it might be a good approximation for this state. But for this state, you see that this is much bigger, so maybe don't use this one. Maybe use a different scheduling. So you can choose now, if I will be applying it to the stage mu, maybe I should use a sequence of D0, D1, D2, in every step a different operator that depends on the mu. And that would be a local eigenstate by eigenstate procedure where the DBI looks at the norm of the off diagonal of the Hamiltonian at every step of the iteration. You optimize how long you go. So sometimes you go long, this is long, and then it becomes short. Yeah, that gives you some sequence of how to schedule this. And you can turn this into a circuit that you apply to your state, and maybe sometimes it kind of fails, but sometimes it might be surprisingly good because 5 step is, this is not big cost to run this. Okay, if there's some questions, that's a good moment to ask. So this is the kind of numerics that we can run. The goal of the reminder is to tell you how to take those recursive equations that we can understand with linear algebra and turn that into a transpiled prescription. So the recursion itself, you cannot run directly on the quantum computer. You need to explain which kind of evolutions to do. And that's what we are discussing with group commutators, and that's what I want to do next. Okay. So what I'm saying is that it will vary state to state. After 5 steps, this 1, 1, 1, 1 state, which is kind of the ground state here, it's like, cool, okay, done, 5 steps, easy. But like for the most excited state, the 0, 0, it might be like still not a good approximation to an eigenstate. There might be much more happening still. Okay, good. So let's continue back and see what does it take to apply those unitaries. Anyway, so we were discussing a few things. I now described more or less numerically what it means to have this eigenstate by eigenstate diagonalization, because different labels mu might give me different eigenstates. And it might be a good approximation, it might not be. So we go eigenstate by eigenstate, and we kind of like wiggle around the procedure so that for every desired eigenstate, I kind of managed to do it more efficiently. I took this variational freedom. Let me tell you one more thing with the formulas, because today the point is also to review LaTeX formulas so everything is clean. After k steps of the iteration, I can take my input state and my rotated Hamiltonian, I can check what's going on, yeah? So I can square the Hamiltonian and take the expectation value of this, or I can take the energy, the expected energy in that input state, square that, and that variable we would call energy fluctuation. And if my Hamiltonian is diagonal, then this is decomposed in Pauli Z operators, and this is a computational basis state, then this becomes 0, okay? So energy fluctuations vanish for eigenstates, and the experimental paper from Innsbruck preparing eigenstates of the Ising model, they were kind of using this measure as well. So basically, you know your Hamiltonian, so you start measuring it out, and this is something you can do, okay? So this is why I was showing this, and that's how you can check on the way. So this can be your cost function that you optimize and so on. What the theory gives us, that's something we will discuss downstairs here, is that it justifies why this is a good ansatz. That's what I started with the handwritten scribbles, why this is a good ansatz. It's a good ansatz, but you still need to do some work to make it like the appropriate ansatz and optimize it out. One thing that I don't like discussing is another way of going about it, because it's more costly, more noisy, and maybe not so helpful. So I could consider a density matrix that I prepare by some purification or some mixing operations and so on. I could do a mixing operations of identity with the couplings of the Hamiltonian. And in principle, I could construct this density matrix. Maybe it's doable that you actually manage to do this. Then if you apply here the dBi rotations here, you start diagonalizing this Hamiltonian, because at some point after k iterations, this will be a hk, and we know hk becomes more diagonal. So basically your task here in this thermal encoding would be to take a non-diagonal density matrix and make it successively more diagonal, okay? And that sounds great. That's what we do in NumPy and so on. But this is diagonalizing everything at the same time. So I give a list of things why I don't like it. If you start measuring this, then this is a small operator because it's bounded by 0 and 1 by this norm. This is something you need to do to ensure that this is a good encoding in a density matrix. So a lot of expectation value will be just complete noise. So you will have to extract everything on top of the noise. It's difficult enough for the eigenstate by eigenstate, so I wouldn't do it too much, I think. This directly goes for the Hamiltonian, and you might think like this is amazing, but it's actually not so good, because let's look at the numerics. Here I will show to you what 10 or 11 eigenstates, and that's already quite many. That's something I learned with the numerics, that selecting those eigenstates is actually like a bit of an art, which one is useful to think about. If I have 10 qubits, this is already like 1,000, or it's quickly you have 10,000 states. And not all of them are equally interesting, and they differ largely in energy, yeah? So this, this state has energy 26, so it sits somewhere here on the spectrum, and this is close to the ground state. So this one is close to the ground state, and it sits somewhere here on the spectrum. Why should I look at them at the same time? I could do eigenstate by eigenstate, and I could study this portion of the spectrum, this portion, this portion, this portion, and I don't need to have them all at the same time. I don't think this is this would be advantageous compared to how difficult it becomes to do it. Yeah, so that's why I go eigenstate by eigenstate just by my choice. I think there would be very difficult things. Even though it looks great, we would diagonalize the Hamiltonian, it's encoded in the quantum state, great fun. But how do you extract those things? And how do you check that you diagonalized? Yeah. Here, this is quite an easy measure. Comparatively, like for the things that you might want to do, it's just the art of measuring correlation functions and putting them together, doing statistics on it, and getting the stuff out. Here, the non-diagonal part is the non-diagonal part of the density matrix. That's a field in itself to study this, and this is like quantum coherence in the states with respect to the diagonal basis. Good luck measuring this. This is more or less like measuring entropy of 200 qubits at once. Yeah, might not work. Akash, question. Yes.
Yeah, so I'm like a bit confused because you had this plot with L, right? You had these 3 plots, right? In the row. These 3 plots you showed recently.
Yeah.
If you go above, so what is the plot? Would you show me?
That's the plot. Or the figure.
Nothing.
Hmm?
Yeah, yeah. I mean the figure. Yeah, exactly.
Okay. So what's the question?
Yeah. So on the number A plot, right? You are changing with the duration flow and it's decreasing, right? So it's fine, like the off-diagonal restrictions, and it is supposed to be. But then we saw this plot before where the off-diagonal terms were not decreasing but fluctuating, right? Up and down with the flow duration.
This one.
Before.
Yeah.
Yeah. So what is the difference? Because it looks like they're like, inconsistent or something, or maybe different settings.
Yeah, yeah, okay, so fine. If so here I'm showing this for the optimized. So basically, if I would look at the norm as a function for that generator, it would look maybe like this. So I just chose this, and that defines for me H1. Now, if I start with this, it will reach the minimum and go here. But this I'm not interested in. I'm interested how much in a greedy way I can get. So as soon as it starts growing, I stop here. That defines for me H2.
Okay. Yeah.
So those curves could be overlaid here. That's maybe an interesting visualization as well. But I would say this is the result of what I was able to sort of train or find out. Like that's some strategy that I could use to furnish this kind of answers. Yeah.
Right. Okay.
And basically by definition, as soon as I choose any as even this one, so I would be somewhere here with this flow duration, I will be just less efficient, no? Because we will maybe not come to this today. Actually, maybe we will. The circuit, if I want to get the unitary U1 after 1 step and unitary U9 after 9 steps, the cost of this and this is like growing very fast in the number of recursion steps. Okay, so those plots are focusing on the expressive power. How much can I do with few recursive steps, because that's the costly part. If you add one more recursive step, it might actually become like you might use up all of your quantum volume. Yeah. So the game with double bracket iterations is to do as much as possible with the smallest possible number of recursion steps. And here I'm still scheduling this according to the global function. And I'm showing that sometimes some states have a better rotation than others. Now, after 5 steps, maybe it could be that I should go longer, and then maybe this will be longer, because maybe going longer actually focuses this one and maybe refocuses that one. Okay, because I'm doing the global thing, I'm not targeting an individual eigenstate. Yeah, so that's a little bit different. We are guided by those analytical equations that we can derive for the global thing. Yeah, but this is showing that for individual eigenstates, mostly this is lifting degeneracies. It's a good sign actually, because the next step will actually go down. So it means that there's some traction in the flow, and and basically something is happening for your eigenstate here. So you just try to continue it longer, and at some point maybe nothing more happens, and that's more or less what it managed to do, because this diagonalization starts slowing down. Yeah, so there are certain issues that we will be dealing with. You see here some oscillations as well, like that. Yeah, so all this stuff needs to be supervised by the user according to the needs of the problem. What we are talking about is how to prepare an eigenstate mu sub infinity, and this you would use to derive some properties of materials.
Right.
But I don't know which property you want, and I don't know exactly what you're doing. So I don't know what kind of epsilon you might want to have. It might be good enough that this method does this and tells you some conductivity is good for some doping. You make the material and then you check experimentally. So it might be just kind of exploring by quantum computation, find a good guidance, guess, and you check it, and then you do it more or less interactively. So so basically all those things if you want to do it very efficient, you care about some implementations, then you have certain constraints which might make it easier for you to optimize other things. So there's no ultimately global methods for that. If you want to speed up something, if you have infinite runtime, then everything is equivalent. Okay, so that was a long detour, but this is more or less how I think those things would play out. Yeah, good. So we have those diagonalization methods, and the important part is that we are more or less doing analytical compiling, in the sense that we have equations that tell us how to compile a circuit. And the circuit will consist of evolutions under the input Hamiltonian and diagonal operations. So I talk about evolution oracles. One oracle could be just do out of small gates Hamiltonian simulation, get e to ith 0, or just apply it. You just say, it happens that I applied it for time sk, done. So I query an oracle and I'm oblivious how this is done. This is the same thing as changing the backend in Kibo, okay? The oblivious oracle. So I say it somewhere here. So the backend in Kibo could be a GPU, it could be NumPy, it could be a quantum device. But you just say, keep applying those evolutions in the sequence, and you do it the way you want to do it. And if you do it properly, then this DBI will do this and that. So that's the oblivious evolution oracle. And now I need to maybe skip a couple of things. But okay, we have the abstract method here. The in between, I'm discussing the monotonicity equation that we derived. So for example, if I rotate my generator by the bracket, I compare those two things, we get the scalar product, this we saw before. So that's kind of our guidance why this stuff should work. And in the end, it's problem specific. So you can prove a corollary to that proposition that for any sequence of d0 until dn, it will diagonalize a bit, but it might not be very efficient. So we get a statement about generic properties of those circuits that they are diagonalizing, but we don't have a statement which choice is the most efficient. This depends on the problem, so I don't say anything about that. Okay, then we talked about the group commutator, and the group commutator approximates a bracket. I think here actually I should have a minus. I'm still fixing those kind of conventions, because in the way you order, the bracket might flip, so you need to do it correctly. But once you have that, you can define the related group commutator iteration. So instead of rotating by E2 minus SW, I will locally here for each step, okay, I will rotate by E2 minus SKWK, and that's approximated by this. So this is a different iteration, but I also call it double bracket iteration because this is approximately the double bracket, okay? Okay. So this is what we would be running. We would be running an iteration on the Hamiltonian to keep repeating the evolution, okay? So how do we do this? And for that, I wrote this big blob here, which would be transpiling the DBI, so the recursive algorithm, into a sequence of applications of circuits. So we would have two kinds of oracles. One oracle to query the different diagonal evolutions. So you give me those decay operators, I can compile them using Hamiltonian simulation. And I need to evolve under the H0 Hamiltonian. Okay, those two things. And now I need to put it together in a sequence because I need to apply this to my input state mu, the computational basis state. So we saw 1, 1, 1, 1 goes down in energy. We need to be able to apply this to a unitary. So what we want to output is an ordered list of queries to say, apply this evolution to this time, or apply a diagonal evolution with decay to that time. A list of those schedulings. And then you go through the list and keep applying it to the state. Once you're done, you should get a state which is the same as if you were rotating the Hamiltonian. So that's our, that would be an implementation of that. And the way we need to do that is that we are dealing with a recursion. So how do you store HK? And let's say in the cache step, I would like to create V, in this notation, it will be RK. So not curly R, regular R, which would be IDK, and E to IHK, E to minus IDK, sorry, and IHK. And they all have some SK on it, SK. Okay, so how do I get this? The way to get that is to say that HK is some VK H0 VK dagger, or the dagger convention is here. So first I need to get this, so I do it recursively. I say, after k steps, this transpiler of the group commutator iteration, after k steps, I just need to get this. So I will pass to you the oracles, and do it please for me k minus 1 steps. Give me that ordered list to do that. Once I have this, I know how to run this WK, let's say. In the transpiler environment, in the transpiler environment, we have actually k minus 1. So k minus 1, k minus 1. So once I have this, I can replace RK to be E to IDK minus 1. No, RK is like that. DK minus 1, I think we should need. Or, okay, in this notation like that, fine. Doesn't matter. And then I will need to do VK E to I H0, but not S0, but K, and then VK dagger. Okay, and this is done here to say, if I want to evolve with E to SK HK, then I need to rotate it this way before and after, okay? And then insert that in the group commutator. So our group commutator is a little bit inflated, and you see this PK is doing everything that we did before. Okay, so that's a very recursive, very repetitive circuit, and that's why the runtime grows in the number of steps. Okay, so that is our transpiler. Let me go through this again. The unitaries that I need to do are all the unitaries before and the step of a group commutator that I need to do. Okay, so in every step of this group commutator DPI, we evolve whatever we had by the group commutator. Okay, so the group commutator is that, and it involves the forward and backward evolutions by decay, and I'm missing here an SK. with a square root probably. So there should be the square root and everything should be in order. But anyway, and to do the evolution under HK, and this is the important encoding, and that's what I call unfolding of the recursion. So normally in NumPy, I would just rotate my matrices H1, H2, Hn, and always use HK, yeah? But on a quantum computer, I have no way of updating how I'm evolving my state. I can only query my oracles. That's why I'm also stressing the oracles. This kind of stuff here I can do, but I cannot just go about evolving here with HK. This is H0 and not HK, and for the reason that I need to say how to do this. And the way to do this is to evolve with H0, but to conjugate it with the previous evolutions. And then we use the formula that if I had VK e to I th0 VK and the dagger here, then I can put it upstairs here VK H0 VK with the dagger here. And this is the evolution with HK. Bam, done. Yeah? So that's the trick that I'm using here. And this is something we would call unfolding, because whatever I'm putting here is actually obtained from the previous steps. So there will be a lot of repetitions. Yeah, that's transpiling. The ultimate point of this is that you see that by this annoying recursion, by this annoying asking, okay, what was this for the previous step, and then adding those lists together, you go down to the bottom when you do 0 steps. That's just identity, you forget that, which means you obtained a sequence of operations that does all those group commutators correctly, but it involves only the basic evolution and only the variational evolutions that you chose. So that's something you can run on a device. And then you do it in the sequence of this ordered list that is outputted by this transpiler. Okay. So I tried to repeat myself a few times. If there's some questions, then fine. Otherwise, this is the best I can do so far to explain this transpiler. In the end, we need to apply this to the state. We were applying this to the Hamiltonian. So the quantum algorithm would be, I forgot to say the input is some state psi0 that we start with, or psi. And then we will get psi k after evolving psi0 with this unitary UK, which means we take the list and we reverse the order because we apply it to the state. And then we apply the diagonal operations, dk and h0. And for every query to those evolution oracles, we get a circuit. We then transpile the kind of evolution oracle into some circuit of primitive gates. That's maybe one more layer of transpiling. You get a circuit that you can deploy, so you make your gates, and that's your evolution T. And then you go to the next one, and next one, and next one. There's a number of those steps that you do, and that will allow you to implement K. So ultimately, you will get this psi K, and we saw numerically what that does. This is like in the number of steps K. Okay. So at the end, maybe after capital K equals 30, you get all those results at the end. Good. That's more or less what I have to say about the transpiling. So that's basically the translation of the equations that guide us how to diagonalize. We knew that we can express all those things in operations that are doable, because if I want to evolve by, in this case, minus AB bracket, then I would order it in this AB way. This is something that I can, in principle, start scheduling. The thing is that now we need to do it recursively. So this is E to ITHK is important, and I'm missing, I think, some outlined equations to explain this a little bit better. I was working on trying to explain in general how to do this, to talk about some frame shifting or covariance under frame shifting and so on. Basically, if my generator is, this equation maybe helps still. So if I have some L J dagger, which is my HK, which is VK dagger H0, VK, then I'm using this formula that exponential of Lj, I can put around the bare evolution of the basic operator. So this is frame shifting, and basically getting some evolution under the frame shifted operator means that I can unfold it here, and I'm kind of covariant because I can put the evolutions here and I will be fine. Okay. So for the dephasing channel, this is an example where this property holds. And if we just put here some known Ising model here, this is not a problem. And then we just do the frame shifting in the group commutator, and then we are happy. So that's some discussion here, how to do it more generally and what kind of channels we can apply and access to it and so on. Okay, let me maybe comment on the runtime a little bit more. Do I have the runtime here? So how many queries to this H0 evolution do I need? So in the group commutator, I will have, let me show the group commutator, skipping through quickly, sorry. There we go. There should be a minus, I think. If I want to do the evolution with the minus here, I need to evolve with the square root here, the evolution minus, I go. So J plays the role of the H0 Hamiltonian or HK Hamiltonian, and D is some diagonal operator, okay? Then I need to do the Hamiltonian evolution twice, and I assume that this D operator is chosen to be something very cheap, so I forget that. So how many evolutions with the input Hamiltonian do I need? Okay, for doing the group commutator, I need to do it twice. So, and we said that if I want to do the previous evolution, I need to repeat everything I did before. So I need to do HK twice, but to do HK twice, I need to repeat everything that I did before. So I get this recursion, and this is just an exponential, okay? So actually, I think I need 4 because the conjugations, but this becomes an exponential. That was the point in the notes. I still need to correct a few things. If I have like a more complicated evolution, my diagonal operation might be depending on the H0 evolutions in the dephasing channel. So I might actually have a worse constant here, and then the exponential scaling means how much I'm also using of those H0 oracle queries to do the diagonal evolutions as well. This is not something you would be doing in practice, so this is more relevant. And so we get this exponential scaling. So basically our transpiler, because of those exponential scalings here, of this repeating that I'm trying to keep track of here, that tells us the length of this transpiling list here. We should expect that the list of evolutions that I will be applying, this will be growing exponentially with the number of steps. That's the bad thing about it. The good thing about it is I started showing some numerics. 5 steps is already good. And there's several things that you can do to fight the number of steps. You want to lower the number of steps as much as possible. So for example, that's why figure 2, because I can, in my current step, go longer, that's still cheap, instead of switching to a new step prematurely. Yeah. So that's why this figure and so on. I think next week we could maybe discuss a little bit the numerics that I did, and that's more or less the status of what we know how to do things. Okay, so good. I think this is all about this figure in the end. The global cost function. The global cost function is kind of optimized by those double bracket rotations. The structure of double brackets gives us circuits that have diagonalizing properties. Then we are optimizing things and going with the minimal in the greedy way here, okay? Then we go chop, 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 and that's reducing the global thing. What does it do to eigenstates? It's not fully monotonous, but you see that you have this tendency of stabilizing the value here, and then narrowing the fluctuation around this so that at the end we get maybe quite nice eigenstates. Yeah. And now the art of this running this on a quantum computer is to translating whatever was happening for HK with this ESKWK, HK, E minus SKWK, and that gives us HK plus 1. How do you translate this using the allowed operations? The allowed operations are the oracles that I listed. That's the rules of the game. That's the transpiler. And it gives us this list of operations, might be exponentially long, but already in the previous version of the manuscript, I talked about pre-compiling. So this you can actually compile. So this will be fine. Then you can do some more steps algorithmically, and then maybe you get some nice results to try to reach maybe here one day. Who knows? It's a big question how to make it more efficient here. That's something like where every improvement makes the cost of this shorter, so you can maybe go further. The longer you go, the better it will be. So any improvements are like very welcome. And what this shows is like how many do you need, how much dependence on those steps you need. So 10 is still quite realistic because you can do the first 5 by Hamiltonian simulation probably, then you do 5 steps. This is maybe 4 or 2 to power 5, but this is still doable. So we might, let's say, my estimate is maybe to do 10 steps would be thousands of gates, but not millions of gates. So thousands of gates is intermediate scale quantum computing. Yeah. Okay. So, but that's maybe the end message. If to run more than 5 steps, we are starting to talk to about tens of thousands of gates, 100,000 gates, maybe something like this might be needed. Okay, and that's still not too bad because for Shor's algorithm, we would need to do a lot of CNOTs for controlled unitary evolutions, and then scalings might be quite big. The nice thing is that 5 steps give you something, and here we are talking about maybe less than 1,000 gates. So maybe that's possible to push it down, but yeah, it's still demanding some operation time. Good. So that's where we are trying to see how to minimize this. Good. Okay.
Mike, like one
Yeah.
thing that about the cost function. So if we have this like variance, right? So when the variance is like 0, it doesn't say that. I mean, consider like any quantum chemistry problem, like Hamiltonian of a molecule or something.
Yeah.
Because it's basically finding the excited and the ground state, right? The problem will reduce to.
Yeah.
So if the variance is like 0, then it gives you the information that you are in a eigenstate, but you don't know which eigenstate you are, right?
Yes.
So maybe like a combination of like energy and the variance would give you like more information, right? If the cost function.
Yeah. Yeah. So that's something you want to run, and that's a problem you are interested in. Then you need to choose this initial state appropriately. But I think for quite many cases of interest, those kind of fully polarized states will have the extremal energies. So it might be that it's a complicated initial state that you need to choose 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1. Or you just try 1, 1, 1, 1, 1, 1, 1. You check if the energy is very low. You give to it some estimate of temperature. For example, you study superconductivity. And if you see that this corresponds to some excitation energy range that is interesting for you, you might not need the ground state. Yeah. For chemistry, you might, maybe, but it really depends on the problem. We are also discussing internally some strategies for lowering the energy and optimizing the energy as well. But in principle, this is this eigenstate by eigenstate case. You give me some computational basis state, that thing will be narrowing the fluctuation, which will be moving that to different energies. So you see this kind of split after 5 steps, which is, I'd say this is cheap. You see that it levels off. There's not much movement of the level here. So you can quite quickly see which way it's going for your initial guess. Yeah. So that gives you more or less where the energy will stay. And then you don't need to optimize the energy anymore. So you need to run this for different input states here and see where the average energy is going. If it's going to the regime, for example, in the spectrum where you would like to have it. So let's say we would like to have this regime, then I would start somewhere here. And if I'm landing somewhere inside of my energy spectrum of interest, then I just continue it in a, so I know that this will be flowing towards that state. So I start strategizing to narrow this instead of focusing on that. Yeah. But I'm not doing this in the paper because this is like too refined and you cannot have like a general enough answer. This is case by case.
Yeah.
Yeah. So energy, choosing energy is important. Yeah. In principle, you might make it interactive that even if you start with a wrong thing, you might want to see that the flow is going down in energy. You can maybe add some Monte Carlo to it, but that's not something I worked out in detail. So I don't have like specific results. I would say more use this fact that it quickly saturates. So then it becomes a straight line quickly after 5 steps or so. Check which one is going down and then reduce the fluctuation here and study the physics property of that state. And physics should be robust to temperature and so on. So you should be able to get some answers. And it might not be that you need really epsilon approximations. Yeah, so maybe being somewhere here in the blob is already enough. That would be good, but who knows? Depends on your applications. If you really need epsilon approximations, it's very big matrices, so might be costly anyway. And we want to get to the bottom of some physics effects, so we might need to change the constraints a bit to make it easier and just focus on what we really want, so properties of materials. Let me finish the recording here. Thanks, Akash, for all the questions, and we can talk some more after.
Yeah.